So, but yes, these are up. And so if we just, actually, let me go back one, just to talk a little bit, to review what we discussed the last class, which was about how fructose 2,6 bisphosphate is one of the allosteric controls for both gluconeogenesis and glycolysis. And it's regulated by phosphofructokinase 2 and fructose 2,6 bisphosphatase, or fructose bisphosphatase 2, whichever that you want to call it. And what's really cool about this that I don't believe I got a chance to point out before, is the fact that it's the same protein, and it's same protein that does both these enzymatic activities, so it's bifunctional. So when one side of the protein is activated, the other side is deactivated. So you can have the PFK2 side activated while the FBPase2 side is being deactivated, and vice versa. And it's one of the proteins that gets phosphorylated by pKa, which what did pKa stand for?
Protein kinase A.
Protein kinase A. And protein kinase A was turned on or activated by what second messenger? Cyclic AMP. Awesome. And the phosphorylation is what activates the FBPase2 and inhibits PFK2. And I'll show that in just a moment. Okay, so this is one of those. Last semester when we did the protein kinase A and the cyclic AMP camp pathway, remember we just said there was a whole bunch of enzymes that gets activated, and one of these is this complex. There we go. So this is this little cartoon depicting that. Okay. And so what happens here is that, I guess, I don't know where the best thing starts. So if we just think about insulin, when does insulin get released as a hormone? Is it when blood sugar is high or blood sugar is low? When your blood sugar is high. And so what it does is, it's disappeared, is it actually activates phosphoprotein phosphatase. Okay, and what do phosphatases do? They take away phosphates. And if it has a really generic name like phosphoprotein phosphatase, that means it's more promiscuous typically. You're going to see this as a player with other phosphoproteins that gets phosphatased. Okay? And so what happens there is insulin, whoops, I circled the wrong one. Insulin activates the phosphatase that will remove the phosphate. And so when it just has the free hydroxyl group, this is when the PFK2 is active, and so you're going to increase the amount of the bisphosphate form, the fructose 2,6 bisphosphate, and it turns on glycolysis in the liver, and it inhibits gluconeogenesis. Why does that make sense? Why are you going to inhibit gluconeogenesis whenever insulin's around?
You don't want it to go back to glucose?
Right, you don't need to make new glucose. I mean, literally, that means glucose new synthesis of. So you don't need to make any more new glucose from endogenously within your body, okay? So it's going to stimulate the liver's glycolysis, because that means you've got plenty of sugar around for the rest of your body tissue, so now your liver can go through glycolysis, all right? Now, on the other extreme is whenever glucagon, which is the antagonistic hormone. So now the blood sugar's starting to wane. It's in between meals or what have you. And, stop doing that. It starts to wane. And so what happens here, this CAMP-dependent protein kinase, that's the fancy name for protein kinase A. Okay? Because it's a protein kinase that's CAMP-dependent. So pKa gets activated due to glucagon. Glucagon causes the concentration of CAMP to go up. The concentration of CAMP is what activates pKa. And as we already know, kinase means it's going to add a phosphate on at the expense of an ATP. And so now that it's phosphorylated, the PFK2 side is inactive and the bisphosphatase side is active. And so now the concentration of fructose 2,6 bisphosphate will decrease. So the liver's glycolysis is turned off and gluconeogenesis is turned on, so that way it can provide new glucose for the brain and for the muscles and things like that. Okay, and so that's why they are antagonistic with respect to each other. But this one's really nice because it's one large complex that has both activities. So when one side's on, the other side is off. And whether or not it's on or off is just due to that phosphate. this is very similar little cartoon to show this, except now we've already discussed in the last class, we discussed how hexokinase is regulated between the liver versus the muscles. And then we just finished up how phosphofructose kinase 1, PFK1, is inhibited or activated glycolysis and gluconeogenesis. Now we're going to do step 10, which remember that's pyruvate kinase. And once again, the liver has a different isoform or isozyme than the muscles. Okay, so I'm going to start with the liver. And so glucagon, well, what it does is it's going to turn on through CAMP, the pKa, which will then hydrolyze ATP, and another enzyme that gets phosphorylated is pyruvate kinase, but it's the liver form of pyruvate kinase, not the muscle form. And so it inhibits it. So it's going to, will that turn on or turn off glycolysis in the liver? Turns it off, which should make sense since your body is saying we don't have enough sugar, so we can't have the liver competing for the sugar resources. Okay? Likewise, this PP, oh, I did it again, I hit the wrong one. You think that the big, I'll just show you. See, this gives you the big one and the little one. It's the little one that you have to point at and talk to. So if you touch the big one, it should be opposite. Okay, so that PP, if you notice, it's using a water and it's kicking off an inorganic phosphate. So what class or classes of enzymes could this be? Phosphatase. And what do you suppose the first P stands for? The second P is phosphatase. No. Phosphoprotein phosphorylase. Phosphatase, the one that I just talked about before. This is another substrate where it just kicks off that protein. Kicks off that phosphate. And so now the pyruvate kinase is active, and that's true for the liver. And well, I did it again. I don't know why. Here. There we go. All right. And then here, everywhere, including the liver, the muscles and everything, we've already talked about how, they are inhibited by ATP. They are activated by fructose 1,6 bisphosphate, and they're inhibited. Why does it make sense that it's going to be inhibited by alanine? Alanine actually can inhibit pyruvate kinase. Why would alanine inhibit it? Under what conditions will you have lots and lots of alanine? Because we can't store it for long periods of time, per se. We'll find out that alanine is a buffer system of sorts. You've just eaten, okay? And so if you have a lot of alanine, what else do you have a lot of already? Because what does alanine go on to become? Pyruvate. So if you have lots of pyruvate and lots of alanine, then you don't need to make more pyruvate. And so that's why it's going to make sense. So alanine is a good indicator of how much pyruvate is around, and also about your general energy levels. Okay, what about acetyl-CoA? Where does the acetyl-CoA come from?
Come from beta oxidation.
It's beta oxidation. That's when you're breaking down your fats. That's the final product before, and it's what goes on into the citric acid cycle. You can also get acetyl-CoA from pyruvate. And then long-chain fatty acids. If you have a lot of long-chain fatty acids, what's that indicative of? When are times that you've got a lot of long-chain fatty acids, if you're healthy? Are your energy levels going to be high or low when you have a lot of long-chain fatty acids? High. Okay, so, right, you're just eating that, or you're starting to break down, triglycerides and things like that. So you've got plenty of energy around, so it's going to inhibit pyruvate kinase as well. Glycogen breakdown we actually covered in chapter 14 with like the debranching enzymes and all that kind of stuff. So you can just go review that. Okay. So we have glycogen that comes from glucose. So now we're going to be building it up. Notice it's glucose 1-phosphate. is the first step. You first have to activate the glucose. You can't just take two glucoses and stick them together and make glycogen. It's not energetically favorable. So you have to activate it somehow. And we do this, I don't really like the old book. We do this by making what's called a uridine diphosphate glucose, UDPG. I don't know why there's a big space, but I can't fix it because it's a picture, not text. And inorganic pyrophosphate. Okay, so what class or classes of enzymes can do this? Like maybe a pyrophosphatase, okay? Right, so yeah, this is the first time I do believe that we've seen something that required UTP, which is uridine triphosphate, and that the glucose 1-phosphate actually interacts with UTP to make UDPG and pyrophosphate. Okay, and then the next one should show. Oh. So this one's a pyrophosphorylase. Okay. And what's it's adding is not the inorganic pyrophosphate as it adds the UDP onto it, because UDP is a great leaving group as well. Give everybody a moment to get caught up. So now that we've activated the glucose, we want to add it onto the growing chain to make, glycogen even larger. Here, okay, so this the way that this works is the new glucose gets added on because the UDP is a great leaving group, as I mentioned before. Okay, and so now it kicks off UDP. Of course, you've got to go back and make your UTP again. And so I'm actually going to cover it first. So if we look down here, the way that we get our UTP back is ATP gives up its phosphate to make UTP and ADP. So what class or classes of enzymes could this possibly be?
Kinase?
This is a kinase, and if you were going to name it, what would you name it? We're actually going to see this enzyme again later on. Because this is also one way that we can get GTP or CTP in theory. Yeah, this is like that nucleoside diphosphate, because technically you're adding it to the diphosphate. So sometimes they call it nucleoside diphosphate kinase or NDP kinase. This is where an ATP gets used up to regenerate. And technically, in theory, you could go backwards and get your ATP that way. It's just that then it would be a futile cycle. Okay. All right, so this is how we get our UTP back to do this again. Since usually, if you're making glycogen, you're going to be making large amounts, right? Because you've got lots and lots of glucose, so you need to make sure you're cycling your UTP. And then we've added another glucose onto the growing glycogen chain. So what class or classes of enzymes are there that could do this? Maybe a transferase. There's another class, actually there's two more classes that I don't know if we've even talked about yet. So this could be a transferase or, whoops. It's a synthase. Have we discussed synthases yet? I didn't think that we had. And so there are synthases. Which what do you suppose they do? They synthesize something.
Are they the same as like synthetase?
That's the next one.
Never mind.
And so then we have synthetases. And there's a slight nuance to these. Okay. Now, I'm sure that there are probably some exceptions out there, but in general, these both synthesize something. But synthetases usually require energy from ATP or GTP. Similar like the kinase versus a phosphorylase. So there's a synthase and a synthetase. And usually synthetases require additional energy. And so that can go into our growing list. The only other ones I can think of off the top of my head that I know for sure that are the oxygenases, like monooxygenase versus dioxygenase. But that doesn't come until later this semester. I'm sure that there are some others that we've overlooked. Okay. And so, yes, this is glycogen synthase, which makes sense. It's synthesizing glycogen. And then, of course, we have to get the nucleoside phosphate or NDP kinase to regenerate the UTP. And then the last thing, which I don't have a picture of, was, remember we have the glycogen, the debranching enzyme? Well, the one, right now, we could only add it in to make really long single strands. Well, the way that we add the branch is through the glycogen branching enzyme. So debranching removes, branching adds in the branch. Those are really simple ones to remember what they do, since I mean it's explicit in their names. We'll talk a little bit about the regulation for glycogen synthesis and breakdown in just a moment. Okay. So this goes way back to last semester with that whole R versus T form. Which one was more active, R or T? R. Remember, it's relaxed versus tense, taut, or tight, or whatever you went to. All right. And so that doesn't. So just typically the R forms are going to be the active forms, or more active versus the T forms. However, with glycogen, with the phosphorylase, with it, so it's adding in adding in onto the unit. I want you to be able to understand why the logic makes sense. Whoops. So glucose, I'm going to start with glucose, actually is an activator to go from the R form to the T form. So why would it make sense if you have a lot of glucose around, you don't need to turn on the phosphorylase? Why don't you want to have the phosphorylase running or operating if there's lots and lots of glucose around?
That would cause more, or you need more energy?
Well, I mean, no, not quite, but close. I mean, what is this phosphorylase doing? Okay, so it would be breaking the glycogen down to make more glucose, and so it should make sense. You don't need any more glucose around since you have an excess of it, and so it's going to cause it to shift from the R form to the T form. Similarly, ATP does that. Okay, and so does G6P, is glucose 6-phosphate. Which, where did the glucose 6-phosphate come from? It's the product of the very first step of glycolysis, which is called hexokinase. And then ATP should make sense, because if you have lots of ATP around, then you don't need to be making any more energy. And so then it's going to shift it from the R form to the T form. Whereas AMP shifts it from the T form to the R form. And so when do you have a lot of AMP around? Pardon? Right, that's one of the major products from ATP breaking down, and so if you have an excess of AMP, then it means you need more energy. But then glycogen kind of has like a halfway, like you could either have it, instead of just having it on or off, it's got another one where it's on, but it's not full max, okay, and that's whether or not it's phosphorylated. And so they actually have 2 R forms and 2 T forms, and it depends on whether or not it's been phosphorylated, okay. And so the kinase adds it on, the phosphorylase kinase. The phosphoprotein phosphatase is what takes it off. Okay? And so the phosphorylated form is really super active. And it's called A. And the phosphorylase B form, which doesn't have the phosphate group on it, is active but not nearly as active. Okay, so that's why it's like fine control. Let me see. This is really slow. And that's what all this is saying. So Remember, the phosphorylase is what breaks the bonds down between the large the glucoses that are stuck together in glycogen. And this is the major control point for glycogen metabolism because it's both in the R and T form and then that whole A and B. And if you just want to think of it as being phosphorylated or dephosphorylated, B is less active, A is super active. Okay. This is just another, I took this, I forgot to write down what paper I took it out of, but I took it out of paper. Something a long time ago, and it's just a little table that helps explain things. One that we hadn't talked about before was calcium. Calcium stimulates the phosphorylation as well, so it's going to activate it, okay, to make it more towards the phosphorylase A part. But otherwise, glucose, ATP, AMP, all that, at least to me, makes sense. I want you to understand the logic behind it. I don't know why it does this backwards. Okay, now the synthase, that's to make more glycogen. It's also subject to the covalent modification through phosphorylation, but it's the exact opposite. And so here, the phosphorylated synthase is deactivated or inactive, whereas if it doesn't have the phosphate, it's activated. Okay, but once again, it's protein kinase, phosphoprotein, phosphatase, what do we want to call them? Those are the ones that are at play here, which should make sense. Remember, the protein kinase adds the phosphate to the phosphorylase and turns it on, makes it more active. So when it adds a phosphate to the synthase, it's going to turn it off to make it inactive. That's why they're going to be the opposite. Similar to the way that we had with the PFK2 and FBPase2. But instead, these are two separate proteins. So that's what this is trying to say. Glucagon, epinephrine stimulates phosphorylation, then becomes inactive. So, yep. Are there any questions? We learned the two new enzymes, synthases and synthetases. Just remember, glycogen synthase is what makes it. Glycogen phosphorylase is what breaks it down until you get to need the debranching enzyme. And likewise, you have to have the branching enzyme to add the branch in. I can't really think of anything else off the top of my head with respect to these glycogen. Okay.